right, so I'm going to be talking today about assimilation of snow data for ensemble stream flow prediction. Before I begin, I'd like to recognize my collaborators on these projects. Dr. Terry Hogue is a professor at Colorado School of Mines, and David, Kevin, and Barik were students who worked on, who did the hands-on work of what I'm about to show here. So HEPEX has kind of an objective of trying to move research into operations. And a lot of the work that I do is focused on that same objective, primarily focused on trying to advance some of the methods of the U.S. National Weather Service. And recently what we've looked at are data assimilation methods and application of satellite data. So in order to try to increase the relevance of this work, we work with the forecast models of the Weather Service. We try to work with the same methods of the Weather Service to make some parallels there. And I also work as closely as I can with the forecasters themselves to understand what their limitations are, what their needs are, what's kind of out of the realm of possibility for them to implement. Again, try to increase the relevance of this work. So the two studies I'm going to be talking about today are, again, assimilation of snow water equivalent data. We did two studies, one located out here in California in kind of a mountainous basin. Here we're assimilating ground-based snow water equivalent. Forecasts out here are primarily produced for water supply forecasting, although they do have some flooding from time to time. The other study took place in the north central area of the U.S. Predictions here are done for a little bit different purpose, primarily focused around flooding, but then there's some low flow forecasts that are important as well as just kind of general stream flow prediction. This second study used the AMP3 snow water equivalent data in the assimilation scheme. So first I'm going to present a few things of what was similar between the two projects, and then I'll go into each project individually, talk a little bit more about the details of each, and show the relevant results from those. So if you're not familiar with the U.S. National Weather Service modeling system, these models are very similar to the models we've already heard about at the meeting here. They're conceptual models that require site-specific calibration. The snow model is the Snow 17 model. It accumulates snow as well as melts the snow, uses temperature and precipitation as the only inputs to do that. The output from the Snow 17 is melt plus any rain on bare ground, and that goes into the Sacramento Soil Moisture County model, which is kind of like a bucket model. It routes water to overland flow as well as through the subsurface, some faster flowing water in the upper zone and slower flowing water or moving water in the lower zone. That then produces a runoff for the watershed, which gets converted to stream flow using the unit hydrograph. So we use these same models for both studies. The ensemble stream flow predictions that the National Weather Service produces are primarily based on climate. So what they do is they initialize their models with the current states of the basin, either using recent model runs or maybe some data along with that. And then they run past weather data from the historical record that spans the forecast window. And they do this for all the data in the record, and they produce this typical spaghetti plot that's shown up here. So when we're doing our analysis as researchers, we're trying to mimic the same process. Of course, we're a little bit limited because we're not doing a lot of hands-on updating that they may do or manipulation of the models. But so we run it more in a little bit more objective way. We do a historical run of the model throughout the entire record, pull out the dates that we're interested in, and we store those states, then go back, initialize the states in the model, and run the historical data to produce an ensemble for each forecast day that we're interested in. And in this case, we're looking at the spring melt period. So we're doing forecast dates of January 1. So basically the 1st and the 15th of every month from January to April. Try to capture that snow season. So when we're generating these hindcasts for just regular ensemble stream flow prediction without the DA, we have one set of states from our historical run, and then we produce an ensemble that's as big as the historical record of temperature and precipitation data. When we're doing the hindcasting with the data assimilation, we're using all the states that are produced as part of the DA. And in this case, we're using the ensemble common filter for both studies, and that's producing 100 replicate states. So rather than trying to reduce this number arbitrarily, we just went ahead and used all the states. And then for each state, we run all of the historical climate through it. So we end up with a quite large ensemble trace, probably larger than it needs to be, but for these initial studies, we just left it as that. So after generating the hindcast for the non-DA and the DA situation, we then are applying some evaluation metrics. And the results I'm going to show you are going to, I'm going to show you the results for simulation of streamflow as well as the hindcasting of streamflow. And I'm going to look at bias, root mean square error, normalized absolute error, typical statistics that you see. And then for the probabilistic forecast, we're looking at the continuous strength probability score, which is a measure of accuracy of the ensemble, the containing ratio, which tells us the frequency with which the observation is contained with the ensemble, and then discrimination and reliability, which you're probably familiar with. I'm not going to actually show these, but I'll just mention briefly what we found. So getting into the individual studies, study 1 was done for the North Fork of the American River Basin in the California Sierra Nevada mountains. And this basin is pretty well studied. It was part of the distributed model intercomparison studies. There's a large number of papers surrounding this basin. As I mentioned, in this case, we're using ground-based snow water equivalent. And the way this work was done is there are 3 snow pillow sites up here in the upper reaches of this watershed. They were weighted and averaged to get a basin average snow water equivalent for this upper zone of the watershed. So this watershed has a pretty large topographic change from the lower end up to the higher end. This upper area is primarily snow dominated. You get very deep snowpacks building up throughout the winter and then kind of a prolonged melt in the spring. The lower zone has a much thinner snowpack. It may have no snowpack in some years, and it's a lot more transient. So this watershed is actually broken up into 2 zones, this upper zone, which is snow dominated, and this is where the assimilation is taking place, and then this lower zone, which is not snow dominated. So when the Weather Service models their watersheds, they apply these models, the Sacramento model and the Snow 17, primarily in a lumped manner, with the exception of when they have a very mountainous basin like the North Fork, in which case they'll break it up into different elevation zones, just like I showed. So they will apply the models in the upper zone and the lower zone, and then the output from those are weighted or routed using some sort of technique to get total discharge at the outlet. So they're primarily concerned with just discharge at the outlet of the watershed. And just a reminder, the assimilation only occurred for that upper basin because that's the only zone where we had observations. It's also the zone that's primarily important for modeling snow. Let's see, the updating frequency was 7 days in this particular study. And as far as quantifying the uncertainty in the forcings, that was based on a sensitivity analysis surrounding 2 parameters in the model that determine the accumulation of snow. One is the snow correction factor, which will increase or decrease the amount of precipitation received by the model. And then the px temp, which is a parameter that determines whether or not the precipitation occurred in the form of rain or snow. The forecast analysis period is April 1 through July 1st. They begin forecasting on January 1st, but they only look at the April 1 to July 31st period, which is the time period during which most of the melt occurs, and that information is then used for water supply planning. We had 26 years of snow data available to do the updating. So when we're looking at our sample size for the hindcast, we have 26 years of hindcast available. 58 years of climate data to generate our ensembles. And then, not to confuse things too much, but there was a secondary objective in this first study to look at the impact of parameters on the model results as well. And so I'm going to show you results from using the operational parameters produced by the National Weather Service, as well as models that were generated using the DREAM algorithm through an automatic calibration method. I'm not going to focus on the difference between those two, but just to let you know that that's what you'll be seeing here in these slides. So moving on to the results, this left-hand side shows the results from just applying the data assimilation and analyzing the simulations of discharge. In all of my slides, I'm going to show the non-DA as blue and then the results with DA as red. So the idea here is looking at the difference between the blue and the red. And over here, just looking at the simulations, we have root mean square error on the top and bias at the bottom. And we can see that we definitely had improvement in our simulated discharge through the use of DA. And that occurred regardless of the types of parameters that we used. Over here on the right-hand side, this is an evaluation of the hindcast ensemble mean. And I averaged all of the forecast dates here together just to kind of summarize the results. And if we look at, say, for example, the RFC parameters, this RFC here, this is without DA, and this would be the RFC parameters with the DA. Looking at the hindcast, we do see a little bit of improvement in the ensemble mean forecast. Through the use of DA, it's definitely not a significant improvement. And we actually have an example here that using this other set of parameters, we're doing worse with the DA, with this DREAM set of parameters, than we would be if we just simply use the RFC parameters without the DA. So these results were a little bit disappointing with respect to root mean square error. However, bias in this ensemble mean forecast definitely was improved with the use of DA. So moving on and doing an assessment of the hindcast in a probabilistic sense, this first plot up here shows the continuous rank probability skill score. Again, that's looking at the accuracy of the entire ensemble with respect to the observation. And then this is being reported as a skill score, so it's relative to just using a climatology forecast. Again, the results were not what we expected. Any value above 0 tells us we're doing better than climatology, and the larger the value of the skill score, the better we're doing. And it's obvious here that the non-DA hindcasts are doing better than the hindcasts with the DA for this particular basin. And down here, looking at the containing ratio, having that larger ensemble that was produced with the DA and using the updating produced with the DA did not improve our chances of actually containing the observation within the ensemble forecast. And there's effectively no difference here between the DA and the non-DA cases. So what's happening? Again, this was kind of unexpected, and at first I thought, all right, what did I do wrong with my statistics? Went through it a number of times, and I thought, well, let's look at the distribution of the forecast and see what it's telling us. So I visually went through and I looked over the probability distribution functions of all the forecasts relative to the observation. So here I'm showing the observation as the pink, and then just for reference, the climatology is shown back here in the gray. So obviously we are doing better than climatology that has a much wider spread, and our forecasts are much narrower and closer to the observation than our climatology. But what's happening when we apply the DA, and I'm just going to use this column over here which shows the DREAM parameters, is the DA is causing our forecast to shift towards higher flows. And in some cases that's causing us to miss the observation as we go in later into the forecast season. So just as a summary, I compared all of these CDFs just visually. About 57% of the cases, the DA actually degraded the quality of the forecast, or the accuracy of the forecast. About 23% of the time the DA made an improvement, and about 20% of the time we didn't see much difference between the hindcast created with the DA or without the DA. Just a couple of additional comments on this particular study. The skill was shown to improve as the season progressed in all cases, which would be expected. We looked at reliability and discrimination, but it didn't really tell us any more than what these other statistics showed us. There wasn't a whole lot of difference between the hindcasts with respect to discrimination or reliability when we applied the DA or did not. We did find that the best discrimination occurred for the lowest 40% of the distribution. Okay, so that was one study using ground-based data, and again, limited ground-based data, but nonetheless, we saw good improvement with simulations, not so much with the hindcast. So I had a student about a year or so ago test the assimilation of Amster-E data in watersheds in the north central US. And so we chose these 7 watersheds. These are part of another study looking at some other satellite data. Snow in this area is much thinner than in the watershed we just looked at, maybe 1 meter to 2 meters at the most. More snow in these northern areas, and then as we get down to the southern areas, it's not uncommon to have a snowfall, have it melt, go for a long period of time without snow, and then receive more snow again. Just for reference, I'm sure you're all dying to know, there's Iowa State University right in the middle of Iowa. The models in these watersheds are applied again in a lump matter, and because we don't have significant topographic relief, this is an image of the elevation here. You can see it doesn't vary much across these watersheds. They simply just apply the models and then lumped across the whole watershed. So again, we assimilated Amster-E data, and this was done on a daily basis or whenever data was available. It was mostly available on a daily basis. We applied some forcing uncertainty to the precipitation and temperature. These numbers are based on other values used in the literature by other folks doing these data assimilation studies. And in this case, we only worked with the RFC parameters. So the Amster-E data has been kind of criticized for having high errors in regions with a lot of topography or a lot of forest cover, kind of typical of that basin in California that I was just talking about. But for better or worse, we don't have that problem in the Midwest US. Here's a picture of Iowa in the middle of winter. It's heavily agricultural land use in this area, so in the winter there's no vegetation. Just open bare land throughout much of it. As you get to the northern watersheds, you do see a little bit more forest cover, but still not like you would see in the Sierra Nevada mountains. Also, since we're treating these large watersheds in a lumped manner, we felt that the 25-kilometer resolution of the Amster-E may not be all that problematic. So we thought, okay, maybe it's not so great in the mountain watersheds, but maybe in an area like the Midwest US, it could actually be useful. Or more useful. Nonetheless, we knew that there were going to be errors associated with the Amster-E. So the first thing we did is we looked at the bias in the data. There's really not a lot of good snow data for this region of the US. There's some co-op data where people collect some snow depth measurements, but there's really no snow water equivalent. There's no ground-based network like you would have in the Western US. So there's really not much to go on. The best source of data we have for snow water equivalent in this area would be the airborne observations that are run a couple of times a year by the National Operational Hydrologic Remote Sensing Center, or NORISC, which is located in Chanhassen, Minnesota. So we took their data and compared it to the Amster-E observations for the same day of their flights. And we came up with this map. So you can see there's quite a range in biases in this data, anywhere from around 100% underestimated to 100% overestimated, depending upon the location. But we needed to come up with an overall bias correction for our satellite data. So we just averaged this as a first step to kind of simplify the process. And we came up with an overall average of about minus 18%, or sorry, 18 millimeters. This is millimeters, not percent. And then we computed a standard deviation of around 30 millimeters and applied that within the DA. In this region of the country, again, the outlooks are primarily produced for just kind of general streamflow outlooks, some flooding outlooks, some low flow outlooks. They're not doing these water supply forecasts in this area. So they're producing, for the ensemble streamflow predictions, they're producing 90-day outlooks. And so that's what we did in our study as well. There are only 6 years of observations from the satellite, so we have a very limited hindcast sample here. We had 61 years of climatological observations, so we have a 61-member ensemble with the non-DA and then 6,100 with the DA. Again, first I'm just going to show you the results from the simulations. This is looking at the mean absolute error normalized by the average stream flow for each watershed, comparing the simulations with no DA to the ones with DA. And in 5 of the 7 watersheds, we did see an overall improvement in the simulations of discharge when we applied the DA. There were 2 where we did not. The Blue Earth River in Minnesota overall is a very difficult watershed to model. It's very flat. The response is not typical of areas that the Sacramento model is typically applied for. And so that just kind of is some modeling issues in that watershed. Clear River, Minnesota is kind of located in that area where there were positive biases in the AMSR-E, and remember we applied a negative bias correction. So in this case, I think it was our bias correction that kind of led to that result there. This is the simulated SWE, snow water equivalent up here from the snow model, and then the discharge from the Sacramento model. The mean of the DA ensemble is shown here in the red, and then the pink area is the range of the ensemble or the uncertainty. And then the non-DA, again, is the blue. I'm showing the satellite observations here as the triangles. So you can see that definitely through the DA there were significant shifts upward in the snow water equivalent that was produced by the SNO 17. So it seems like there's kind of a low bias in the SNO 17 model as it's applied for these particular watersheds. So I think there's some things that could be done here just with the calibration of that model. And that's kind of corroborated with the discharge data, which is shown here on the bottom. When we applied the DA, we definitely got much closer to matching these observations, which are shown here as the black dots, as opposed to the simulation that didn't use the DA, which very much underestimated all of those peaks. So again, just reiterating that we saw some pretty good improvements when we applied the DA just for simulation. So going to the hindcast, I didn't have too much time to delve into the results of these yet, so I just kind of picked out a few things to show for this talk. Generated hindcast in the same manner as before. This time it was a little bit different because we're not looking at volume forecasts. So as a first step, I just picked out the predicted maximum flow during the 90-day period. The forecast date is shown here on the bottom, and then this is the rank probability score on each of these plots here. So again, some mixed results. In some of the watersheds, we did see improvements. With the DA, we go from having no skill over here in the St. Croix River to around the mid-February, we're starting to see some skill when we apply the DA. In the Pecatonica River, which is a very well-modeled watershed, it really didn't make any impact whatsoever on the skill of the hindcast with respect to this particular variable. And then in the model, in the watersheds, this Redwood River one, for example, and the ones that were very poorly modeled, again, we didn't see much impact. So the DA didn't overcome some of the difficulties of modeling those watersheds. How much time do I have? I'll try to wrap it up here. This is just looking at the forecast on a daily basis and just looking at the bias in the ensemble mean and how that changes over time. I looked at all 7 basins. For the most part, the DA didn't have much impact on the ensemble mean, the bias in the ensemble mean from the hindcast. This is the one watershed where I did see some improvement. This is the North Raccoon in Iowa. You can see a little bit of improvement in this February 1 hindcast kind of early on. Not so much here. It almost makes it worse here for this March 1 hindcast. There's something weird going on here at the beginning, probably because all we're doing is adjusting the SWE in the model. There's a little bit of spin up that's needed to get kind of the rest of the states up in line. But I haven't had too much time to kind of look at the different states and see what's going on there. So to summarize then, we've seen improvements in simulated discharge in both of our DA studies, and there's plenty of other studies out there in the literature that show the same thing. We did find an apparent low bias in the SNO 17, which I think would be important for kind of improving the calibration in that region. However, we didn't see very many examples of where the DA really improved the performance of the hindcast. So that kind of leads to the question, will DA have much of an impact on these types of forecasts? These are long-range forecasts, primarily a function of climatological data. You know, will DA really have much of an impact on these types of forecasts? I would like to go back and look at a shorter-term forecast, maybe use some numerical weather prediction data to see if on the 2 to 3 day time scale, if we can actually see some improvements through the use of DA. So I just want to conclude with this note here that oftentimes we assume that if we just have better models, better data, better methods, and we can improve our hydrologic simulations, that's automatically going to lead to better forecasts. And as I go through my work, I'm finding more and more that that's really hard to prove. It's really hard to come up with examples where we're improving the forecast through these advanced methods. And the big question is why? What is wrong? Are we not looking at this correctly? Are there so many structural errors in the model that we just can't overcome until we improve the models themselves? The technology is just not there yet. And if we can't prove this, how are we going to move operations forward? I can't go to the National Weather Service with these results and say, hey, you really got to implement data assimilation and use this satellite-based snow water equivalent data, because they're going to look at this and there's nothing there for them. And so in my work, that's a huge challenge that I'm not quite sure how to overcome yet. Anyway, with that, if there's time for questions, I'll take one.
Thank you.
Thank you for the presentation. The simple question is, on the western side, you use the snow pillows in order to promote sensing. Why didn't you use RMC, ANSRE in the western side? Was there a certain reason, or because you have ground data, better assimilating ground data?
Well, so that's an older study, number one. So I think at the time, just looking through what had been done, there wasn't a lot of support for using the satellite data in that region because of the topography and just errors with the forest cover. We would like to go back and try the satellite data there just to see what would happen.
You had a chance to try.
Yeah, and actually I'm talking with Kevin right now to see if he can get some money for a student to do just that, because that would be an interesting contrast.
We have had the same problem, and we tried to replace the H-SAF model with satellite-derived snow-covered area. And we got some positive results and some negative results, so sort of even out of certain points. And that was actually an inspiration for constructing the new hydrological model, where we reduce the number of calibration parameters.
Yeah. So I haven't thought so much about that with respect to the SNO 17, but I think you're right. I think there's ways that we could reduce the amount of calibration even for that model. But in some of my other work, we're looking at applying satellite-based potential evapotranspiration data in the Sacramento model. And it reaches a point where there's just no sensitivity to increasing values of PET. And so that tells me there must be something wrong with this model, and some sort of limitation hardwired into it that really needs to be addressed. So I agree with you more and more. I think we need to look to these models and the structures of the models and improve them first.
And how many integrations?
So 17 has 4 that are very sensitive, 4 that are kind of minor. Sacramento has 13 primary ones. So it's a large number of parameters. Mm-hmm.
I saw in the results that some of them, for example, mean errors, they are very, very similar to each other. And I was curious if you were doing or if you applied kind of an analysis, like analysis, or not?
I didn't do that, but I looked at it for the deterministic statistics very briefly, and there's not much it's hard to see a statistically significant difference. So the results are effectively the same for a lot of this. Mm-hmm.
Okay,
good point.
Thank you very much. I'll call on next speaker.